of the talk. So, and the first talk is given by Karthik. So please.
Thank you. This is joint work with Vincent. You're going to hear his name a few times in this session. So this is Inapproximability of Clustering. In order to motivate hardness of approximation for clustering, let's look at the structure of computational problems. It's the landscape. And we have very low structured problems like circuit SAT and CSPs of large arity. And then we were able to prove the PCP theorem. So we could prove the hardness of approximation of label cover. And then we were able to prove something for more structured instances, set systems like set cover and max coverage. And then we were able to get locality. So we were able to prove things for 3-SAT and 3-LIN. And on top of that, we started then addressing graph problems like max cut, independent set. And we were able to get in approximabilities here where you have a graph, actual graph as input. And then after all these things lie these geometric problems, which have at the heart both the graph structure, but an additional geometry on top of it. And this is where our understanding sort of is quite bleak. In fact, even to understand just the graph problems, some of the graph problems like vertex cover, we needed the unique games conjecture. We don't really completely understand them, but fine. After assuming the unique games conjecture, we more or less understand how all these graph problems look like. And yet, these geometric problems are still out of reach because all the techniques developed are for graph problems. And so in this talk, we are going to address one such geometric problem, which is clustering. And the way we are going to do it is we knew from unique games conjecture that the maximization of vertex cover problem is hard to approximate. We have tight inapproximabilities. Then we're going to take this vertex coverage instance and embed it to a clustering. So that's the whole talk. So now I can actually start with what is clustering. So you have points in space, and you want to sort of classify them. So you want to classify them into small buckets. And this is basically the task of clustering. So informally, clustering is the task of classifying the input data. And now we are going to make this formal. Think of a metric space. So you have some discrete set gamma, or it can even be continuous. And you have a distance function delta. And your input is some subset of the metric space, say x. And what you want to output is a classification of x. So as classification, we define it as a tuple, C and sigma, where you're given, you want to pick some centers from your metric space, say C. You want to pick k centers. K is given as part of the input. And what you want to find is a mapping for every point in your input set x. You want to map it to one of the centers that you had picked. And you want your mapping to be good, whatever good means. And we're going to define what good means later. But this is the input and this is the output. So this is the computational problem of clustering. And this is what is known as the continuous version. Because you're allowed to pick centers from anywhere in your metric space, C. But there's also a discrete version in which you're not allowed to pick your centers from anywhere in gamma, but from a subset which is given as part of the input. Because you have some intuition as like, these are the candidate centers I want to pick from, and you want to pick k of them from there. Okay, so these are the two variants of clustering. And now I want to define what good means. So really, this is a modeling question. So it's where clustering is applied. That's from which it comes. And there are several different objectives that are there based on geometric intuition that people have come up with. We have k-means, k-median, k-center. I'm not going to define all of them. I'm going to define k-means and k-median. In k-median, you want to, for a given classification, its cost is basically look at every point in your input data set and look at the center it's mapped to. So compute the distance, and you're going to just take the sum of these distances. So this is k-median. K-means is just the sum of distances square. And this has geometric intuition, at least in the Euclidean metric, because if your points were spherically compact, then this sort of objective minimized is going to map to the right clusters. And in general, how does a computational problem look like for some objective lambda? Then we say in the yes case, there is some classification. So you can partition your point set into k parts such that the cost is at most beta. And in the no case, for every classification, you have to pay at least 1 plus delta times beta. So this is the kind of problems we are looking at. Okay, and clustering is a hard problem. So even when k is 2, it's NP hard. Or we can also look at so the parameters in clustering is k, the dimension, and the metric space. So when k is 2, it's hard. When the dimension is 2, but you allow k to grow, then it's hard.
Are you referring to specific clustering criteria to follow?
No, so this is like, I'm specifically k-means and k-median. So the rest of the talk is going to be just about k-means and k-median. And we also know that in general metric, it's W2 hard. So even among NP hard problems, it's in a higher hierarchy. So when we can't do exact computation, we go towards approximation. And there is a 9 approximation algorithm, and this regardless of the metric for k-means. And for k-median, it's 2.67. And now if we look at a specific metric, which has a lot of structure, say the Euclidean metric, then we are able to get something better than 9, which is 6.357. And if you fix the dimension to be some constant, then you have a polynomial time approximation scheme. Or if you fix k, you also have a polynomial time approximation scheme. So if you fix one of the two things to be some constant, then we have a p-TAS. So with respect to approximation algorithms, we haven't completely understood it, but there is some progress. And now we look at the other side of things, which is the hardness of approximation. And here, let's differentiate between the discrete and the continuous. So for a general metric, from a straightforward reduction from set cover, we know that we can get non-trivial inapproximability bounds, like 3.94 and 1.74. These are not matching the algorithms, but they are there. They are somewhere there, above 1.01, say. But as soon as we go to the LP metrics, things become very bleak again. So here, k-means, k-median, all of them we just know is like 1 plus epsilon for some very small epsilon. And for L infinity, again, we hope that L infinity has such rich structure, we should be able to do something, but like, no. In the continuous version of things, this was a long-standing problem, and then it was only recently addressed, and our best answers are like 1.0013. So in this paper, we were able to improve these bounds. So in particular, for instance, for the L infinity metric, we're able to match the general metric. And we're able to get some improvements, at least in some orders of magnitude, much more than what was there before. So I'm going to put this in a slightly nice table. So as you can see, for L1, it's like 1.56 in k-means, which previously it was much worse. And for continuous as well, we can get 1.07, which is like magnitudes better than what was known. But it's not really the results that I'm so interested in. It's like, it's the proof technique. So we come up with this new embedding framework to sort of get strong inapproximability results. And this is the thing I want to sort of highlight. So without further ado, let me show you a proof. Let's consider the Hamming metric and the discrete setting. So we are given as input a point set X and a set of candidate centers, S. We are in, say, O of log n dimensions. So we have n points in O of log n dimensions. Then we show that under unique games, it's hard to distinguish between the following two things. In the yes case, you have a classification such that the cost of the k-means is some n prime. And in the no case, the cost for any classification is at least 1.56 times n prime. So this is the kind of result I want to show now. We do a reduction from, as I said, vertex coverage. So what is this problem? You're given as input a graph G and a parameter K. And your goal is to sort of pick K vertices in your graph such that you cover as many edges as possible. And under the unique games conjecture, we know that in the yes case, you can cover everything using k vertices. And in the no case, you can cover at most 0.9292 fraction of the edges. And this is tight because there's a STP which matches it. So we have sort of understood vertex coverage, and we're going to embed these graph instances into the clustering thing. So the idea would be to embed edges to data points and vertices to candidate centers, because you want to then pick k vertices, which are k candidate centers, which cover all the data points. So let me put this in a picture. So we have edges on one side, and you have vertices on the other side. And what you want to do is sort of come up with, replace every edge with a point in the metric space, and replace every vertex with a point in the metric space, such that you have k blue points, which are sort of, and you have, for every red point, you have associated to one of the k blue points that you have picked, such that the distance is sort of 1. And in the no case, if you didn't cover the edge, then you pay distance, say, close to 3. And this is the high level. And you want to sort of do this embedding without look. So every edge wants to become a point without looking at other edges or vertices. So this is this notion of non-interaction when you do the embedding between edges and vertices. And this is accurately captured in a communication game, which we call the vertex edge game. So you have Alice and Bob. Alice has an edge, Bob has a vertex, and only Bob can send messages to Alice. They both share public randomness, and their goal is to determine if this vertex covers that edge, or in other words, if this vertex is contained in that edge. So this is a simple communication game, and we are going to show how this game sort of gives us the embedding we want. So there's a trivial deterministic protocol. Just Bob sends his vertex, which is O of log n bits, to Alice, and you have it either covers or it doesn't cover. So you have completeness 1, soundness 0. Or we can do something better by using randomness, which is we send a constant which is dependent on epsilon, number of bits. And in the completeness, you have 1, but soundness is epsilon. So as you send epsilon close to 0, you're still sent only a constant number of bits, but you get arbitrarily close to 0 soundness. And we're going to show this protocol now. So let C be an error-correcting code over FQ. So it takes log n elements and then maps it to C log n. Alice and Bob will randomly pick a location in the encoding, say call it I. And then Bob sends the encoding of his vertex at location I, which is just a field element. So it's in FQ. And Alice checks, Alice has 2 vertices because Alice has an edge. Alice encodes both of them, both of these vertices, and just computes the ith location. So it's 2 field elements. Now Alice just checks if the field element she got from Bob is contained in this one of these 2 field elements. So the message length is clearly just a field element, so it's log q bits. And the soundness is the distance of the code, because if they did agree, but we know that they are different code words. So in the yes case, it's fine, the completeness is 1. But in the soundness case, suppose that Alice had an edge which is not covered by Bob, then you have 3 different code words. And this code word can agree with any of those 2 code words on at most 1 minus delta of the location. So by union bound, it's at most 1 minus 2 times delta of the location. So we get that it's at most the soundness is, the accepting is 1 minus delta of the code. And if you use algebraic geometric codes, this is roughly 1 over square root q. In other words, you can pick a large enough q, which is constant still, and the soundness goes arbitrarily close to 0. And how are we going to use this protocol? We're going to construct a mapping. Say, let's start with the vertices from v to q times c log n. C log n was the rate of the code word, so it's the length of the code words, and we're going to multiply it by q. How is that? So think of it as c log n blocks, and each block is of size q, which represents the characteristic vector of the field element. And once you fix the randomness, which is I, which is the coordinate you're looking at, then you just put a 1 in the location which corresponds to the field element on the ith coordinate. So it's just a simple encoding using the characteristic vectors for field elements. And now your set of candidate centers is just take this embedding and you get it. And for the edges, which you take, okay, so I have 2 vertices now. So you take this or that, bitwise or of that. And the intuition is for every I, there are 2 field elements I have. And I'll accept if Bob sends me one of these 2 field elements. So it's an OR. And that's why the bitwise OR captures this. And now you can already see intuitively that if I did send, so Alice has 2 locations for every block in which she is 1. Everywhere else she is 0. And Bob has 1 location. And if they both, if Alice did send the right thing, then these ones cancel out. So you pay distance 1. And if they didn't send, then you pay distance 3. So this is how the gap of 1 versus 3 comes in if you cover and don't cover. And now we just run through the completeness and soundness. Suppose there was a vertex cover. Then you look at the embedding, which we just did, and construct an instance of clustering, k-means clustering. And now the candidate centers are just look at the vertices of the vertex cover, and you have these to be the candidate centers that you picked. And the classification is for every edge, you need to choose one of the 2 vertices. But one of the 2 vertices, by definition, is part of the vertex cover. So clearly, there is candidate center which corresponds to one of the 2 vertices. You map to it, and you're paying only distance 1 on every block. So because it's covering just from the completeness property. And so if you compute the k-means objective, for every point, you're mapping to a cluster center where you're paying distance 1 on every coordinate. And in the soundness case, you take any classification, and because a classification is k-centers, you build a vertex cover. And now you look, because we know it's a soundness case, there is a fraction of edges that are not covered by the k-centers. And for each of them, you're paying distance 3. So if you do the math, it's like we have 0.9292, so the remaining are paying distance 3, and this is how the 1.56 comes up. Just to say a few words on the other results we have. So this is for Hamming metric. How do we get it for all other metrics? We introduce a notion of graph embedding. So we study embedding complete graphs, the edges and vertices of the complete graph in LP metrics. And the distortion of this embedding sort of gives us the result for other metrics. For L infinity, we can really get strong ones because we're able to study hypergraph embedding. And here, instead of using vertex coverage, we use hypergraph vertex coverage, which was already shown in literature to be as hard as set cover. So we are able to get stronger embeddings here. For the continuous case, we take the same construction we did, but just throw away the candidate centers. And you show that any optimal solution, from that you can decode back the candidate centers. So you get a vertex coverage instance back. Okay, so the key takeaways is you have improved inapproximability for k-means and k-median in LP metrics using the transcript of this membership protocol we gave, and geometric realization of complete graphs and complete hypergraphs. So this is the takeaway. I just want to briefly mention a future work which sort of builds on this. So we have this picture. We introduced in a more recent work a hypothesis called Johnson coverage hypothesis, which is a generalization of vertex coverage which captures set systems. And from this, we're able to get tight inapproximabilities to clustering. In very simple words, this is where you have as input a bunch of subsets of size t over the universe n. And you want to find subsets of size t minus 1 which cover these things. So instead of finding vertices, you want to find subsets of t minus 1 which cover it. And the conjecture is that this approaches the 1 minus 1 over e, which is known for max coverage. And what can we show from this is that we can get, even for the L1 metric, it's as hard as a general metric. So L1 metric with all its amazing structure is still as hard. You can't solve it any easier than the general metric. And the question then is this conjecture true? There is very deep connections to extremal combinatorics, Turan numbers, which have been studied for 60, 70 years. And so this is explored in a more recent work. Thank you.
Questions?
Is more recent work available?
I can send it to you.
Okay.
It's available by email.
Okay. That's a good method.
Is another question with that?
Yeah.
So, about the L infinity, is it like L infinity just case of J on the matrix space?
We are in log n dimensions. So L infinity using the Frechet embeddings is in n dimensions. Yeah, all the results are in log n, so which is like tight because if you go below log n, you can get sub-exponential algorithms. So it sort of contradicts ETH.
So, other questions? No? So, thanks again.